Okay, so now we're ready to solve a linear congruency. So remember, this is what we're looking at the beginning. We have an equation like this that we're trying to solve for x. All right, so to help us solve for x, we need to find the inverse. Okay, so let's look at example 3. So what are the solution to the linear congruency 3x is congruent to 4 mod 7? So the goal is to figure out all values of x that will make this congruency true. Okay, so first step is to find the inverse of 3 modulo 7. Okay, so this number that appears before the 3 and the mod. So we want the inverse of that because we're going to multiply both sides by that inverse. So we saw in example 1, okay, that the inverse of 3 mod 7 is equal to 5. Right? It's actually 5 plus or minus any multiple of 7, but we're just going to use the first non-negative integer there. Okay, so want to find the inverse, we're going to multiply both sides of the congruency by that inverse. So multiply both sides by 5. So we have 5 times 3x is congruent to 5 times 4 mod 7, which gives me that 15 times x is congruent to 20 mod 7. Okay. Now we need to remember one of the rules that we saw in a previous section. So the previous section says that if A is congruent to B mod M and C is congruent to B D mod N, then AC is congruent to BD mod M. Cool, and this works in reverse too. It's like a if and only if thing, right? So we're going to, right here, we have them multiply together. Okay, so it actually, that's basically what we're doing. We're looking at it backwards. Okay, so what we have here is like this product, and we're gonna split it up. Okay, so what I know is that 15 is congruent to 1 mod 7. So we know this one is true. Okay, because you can see that 7 divides into 15 minus 1. And we set it up this way by finding that inverse. So because we found the inverse of A equals 3 to be 5, when we take this product, that's always going to be congruent to 1 mod 7. Okay, so what remains here, so this is like this part right here, what remains, the other part now, is going to be that x has to be congruent to 20 mod 7. Okay, so basically when you put them together, then you're going to get this one. Okay, so we can split it up. All right, so this helps us find x. So basically, what solves this linear congruencies is all the x values for which this is true. I can actually simplify this. We're going to simplify this because 20 is bigger than 7. This is going to be 6 mod 7. All right, so if you basically, you subtract a couple of multiples of 7, so subtract 7 and 7 again, or subtract 14, you get 6 mod 7. Okay, so this means that x equals 6 plus or minus any integer of k would solve this congruency right here. Right. So this is the process of solving congruencies, linear congruencies. You first find the inverse, you multiply both sides by the inverse, then this lets you split it up. So kind of this product of A hat and A is always going to be congruent to 1 mod 7, because that's what the inverse does. And then what's left over gives you an equation for x. So x has to be congruent to whatever is left over, the 20 mod 7, which you can simplify and figure out what x is. All right, so you can check. All right, so let's check. Let's say if 6 is true. So if I plug back into the original equation, I'm going to say, is 3 times 6 congruent to 4 mod 7? And 18 is congruent to mod 7. And this is true because 7 goes into 18 minus 4. 7 divides into 18 minus 4. Okay, so this is how you solve congruencies, a linear congruency. All right, so now we're going to go to, let's look at this problem. This will lead us into solving systems of congruencies. So in the 1st century, Chinese mathematician Sun Tzu asked, there are certain things whose number is unknown. When divided by 3, the remainder is 2. When divided by 5, the remainder is 3. And when divided by 7, the remainder is 2. What will be the number of things? Okay, so I want you guys to sort of pause the video and try this. It's kind of like a puzzle. Try to figure out. So you're looking for a number, right? That when I divide it by 3, the remainder is 2. Right, so when I divide the same number by 5, the remainder is 3. And when I divide that same number by 7, the remainder is 2. So you can sort of guess and check and play around and see what the number is. All right, did you come up with 23? Okay. Again, systems with solutions to systems of congruencies are not unique. They can be sort of any multiple of the mods of the mod number, although we can see there isn't just one mod number here, so there's kind of a combination of things, so it's a bit more complex. But 23 works, right? Because if I do 23 divided by 3, so if I do 23 mod 3, right, it's going to give me 7 with a remainder of 2. If I do 23 mod 5, I'm going to get 3. And if I get 23 mod 7, I'm going to get a remainder of 2. So that works, okay? But we need a strategy for solving the systems without guess and check, especially if you have larger integers. All right, so guessing and checking is good if the number is small, but if the numbers become large, then it's not so easy to guess and check. So we're going to look at an algorithm for how to solve a system like this, called the Chinese remainder theory. Okay, so let's look at this. So this outlines the method. So basically it says if M1, M2, Mn are pairwise relatively prime positive integers greater than 1. So these are the mods. So notice that we're looking at pairwise relatively prime positive integers. And A1, A2, An are arbitrary integers. So those are the numbers that go here. Then we have the system of equation. This theorem says that this kind of system has a unique solution modulo M, which is the product of all the separate mods, right? So that means there's a solution X where X is positive between 0 and less than that big modulo. and all other solutions are congruent modulo m to this solution. Okay, so we're still going to have an infinite number of solutions that we can take this lowest positive value and we can add and subtract a multiple of this big modulo, but we're going to look for the smallest positive solution. All right, so the algorithm, we first find these mk modulo, which are basically the product of all the moduli divided in turn by each of the single moduli. Then we're going to, step 2 is to find, solve for inverses. So we're going to find the inverse of each of these big M's with the modulus that we divided out of the product. Then we're going to form this sum, and this sum is going to give us our solution. So the sum are the products of the A1s, M1s, and Y1s for each of the equations, for each of the little moduli here. All right, and basically this x might turn out to be a number that's larger than the product of the moduli, so we're going to simplify it so it becomes smaller. So we want it to be the smallest positive answer for that's possible. All right, so let's look at this example 5, and we're going to show the steps of how this method works. So let me go here and identify all the different parts. Okay, so this is the same problem that we kind of did by guess and check. We know that the answer is 23. Okay, so I see that I have my separate moduli are M1 is 3, M2 is 5, and M3 is 7. Right, so I'm going to first form the product of all these. M is 3 times 5 times 7, which is going to be, I think it's 105. So 3 times 5 times 7. Yeah, okay. And then we need big M1. So big M1 is the product of the moduli divided by the first modulus. So 105 divided by 3, which is going to be 35. And big M2 is going to be the product of the moduli divided by the second modulus. So 105 divided by 5, which is 21. And big M3 is going to be the product of the moduli divided by little m3. So it's going to be 105 divided by 7, so it's 15. Okay, now we need to find some inverses. So we're going to find inverses. And these are going to be our y values, yks. Okay, so basically we're going to find inverses of each of the big M's paired up with the little m's. Okay, so to find y1, we want to find the inverse of 35 modulus 3. Okay, so basically we're pairing up the big M's with the little m's. So we have like 3 of these pairings, and we're going to find these 3 inverses. When we find the inverse by, okay, you can do it by inspection, or you can do it with the Bezout coefficients. So let's go through the Euclidean algorithm. So 35 is 35 divided by 3. We get 3 times 11 with the remainder of 2. And when we get 3 equals 2 times 1 with the remainder of 1. Okay, you can see that their remainder of 1 means the GCD is 1. And then we're going to solve for this. 1 equals 3 minus 2 times 1. Plug in for 2 from here. So it's going to be 3 minus 35 minus 3 times 11 times 1. We're going to simplify, collect like terms. So we have negative 1 times 35 plus, let's say we have 11 and a 1. We get plus 12 times 3. Okay, so I'm looking for the inverse of 35. So this is my answer. That's the Bezout coefficient that I want. So I'm going to put y equals -1. So you can use the -1, or you can remember that you can add any multiple of the mod that you're working on, or you can sort of add 3 to it to get into the first positive one. So I'm going to actually do that. I'm going to say -1 plus 3 is +2. Okay, but if you work with the negative or the positive, you're still going to get the same answer at the end, right? Okay, so now we're going to find the inverse of the second. So this m2 with little m2, so I'm going to find the inverse of 21 modulo 5. Okay, so same steps. So 21 is 5 times 4 plus 1. So this is the end. We're going to solve for this. 1 equals 21 times 1 minus 5 times 4. And the coefficient of 21 is 1. So this is my y2. So my y2 equals to 1. All right, that wasn't so bad. Now the last one, find the inverse of m3 with m3. So 15 modulo 7. Okay, so 15 equals 7 times 2 plus 1. Okay, we solve, we get 1 equals 15 times 1 minus 7 times 2. So the inverse of the 15 is 1. So my y3 equals 1. Okay, so we find those inverses. Okay, then to find our value of x, we find the sum. We're going to do a1, m1, y1, a2, m2, y2, a3, m3, y3. Okay. All right, so let's put the numbers together. The a's are the numbers that appear here, the 2, 3, 2. So we get 2 times 35 times 2, 3 times 21 times 1, and 2 times 15 times 1. Okay, so let's figure out what that is. 70 times 2 is 3 times 21 plus 30. We get 233, and that answer is in mod m, which is the product of everything. It's a mod 105. All right, so now we want to simplify this because we want our x to be positive, not equal. We want to be positive lower than the m, lower than the product of all our separate moduli. So we're going to basically find the remainder. So divide 233 by 105, we get 2. And find the remainder. So 233 minus 105 times 2. We get a remainder of 33. So this is congruent to 23 mod 105, which gives us x equals 23. Okay, so again, this is an answer. This is the smallest positive value that fulfills all those congruencies, right? But we can add and subtract any multiple of 105, and those will also be answers. Okay, so this is like the formal process, the Chinese remainder theorem, that we'll find from the same number as we did by guessing and checking.